I'm going to do a couple more u substitution problems that are a little bit less traditional. So again, just to review, with u substitution, you have to kind of take a look. A lot of times, if you have something in parentheses taken to an exponent, and you're doing an integral of that, a lot of times what you're going to want to do when you do your u substitution is whatever's in the parentheses is what you want to call u substitution, what you want to substitute for u. But before you do that, just eyeball what else is left, look at the derivative of what's inside, and see if you see that derivative sitting there. Like this problem right here, derivative of what's inside is -5 dx. I don't have any other variables. And I have that just little dx sitting there. Okay, so that would be the perfect u substitution right there. Is just take what's inside the parentheses, set that equal to u, and then do the derivative. Okay, and sometimes it's a little bit disguised. Like you might have, like let's say you have, I don't know, sine squared of x and cosine of x sitting there. It might be harder to see it like that. First thing is, whenever you're working with trig, change the format so that it's easier to see. So instead of writing sine squared of x, I think it's easier if you write that using notation with the squared on the outside. To me, that's easier, because if it's written like I have in pink, it's a little bit easier to see that's exactly what the situation we have above. And so I have something in parentheses taken to an exponent, and the derivative of that thing is sitting right out here. Actually, I should have my little dx right here. dx, okay. So that's your u substitution. But it's harder to see when it's in this format, so sometimes it's easier if you'll change all your trig, use some parentheses, put your exponent on the outside. All right, so that's the more traditional ones. Oh, I also wanted to mention that holds true for if you have a radical. So let's say I have the square root of 7x squared minus 5 or something like that. Okay, you're going to treat radicals just like you do parentheses. So if I look what's inside this radical, the derivative of it gives me 14x, but it is x to the first, and I do have x to the first sitting right here. So again, radicals and parentheses, that's a great place to start, is go ahead and take whatever's inside and do your u substitution that way. But there are some oops, I'm just trying to move it. Right. But I want to talk more about trig. Sometimes with trig, so let's say you have secant of theta, tangent of theta. Oh wait, I don't want that. That's not what I want. Whoop. Sorry. Let's say I have secant square root of theta, tangent square root of theta, and then under here I have the square root of theta. All right. So in this case, you have no parentheses, you have no exponents, and you do have some trig involved here. So you're trying to figure out, well, what should I call u to make this easier? Well, if there's no exponents involved, there's no radicals involved, then another common thing you're going to want to substitute is for the angle itself. So the angle of my trig expressions are all the square root of theta. So that's a good u substitution. And then just before you work with it, remember, change it to exponential notation. Theta, by the way, is a variable. It's just like x. If you don't like theta, you can take all the thetas out and put x's in its place. But it's just common variable when you're talking about angles. So u, if I make my angle equal to u, now the derivative is 1/2. When you subtract 1 from the exponent, you get -1/2 d theta. So when I do my u substitution, I have the secant of u, the tangent of u, and then I have basically this 1 over square root of theta I have to take care of. Oh, you know what? When I write these problems, I keep leaving out my d theta. Should be there in the original problem. Okay, so I have to substitute. Here's what's left that I have to substitute for. All right, so let's look at what that is. That's 1 over the square root of theta d theta. And if I write that a different way, that's theta to the -1/2 d theta. I mean, that's what it means. And so if you look down here, that's exactly what I have here. I have theta to the negative 1/2 d theta. So all I need to do is get rid of that 1/2. So I'm going to multiply both sides by 2. And I get 2 du. That's what's equal to theta to the negative 1/2 d theta, which is 1 over the square root of theta. So in my substitution, instead of that d theta over the square root of theta, I'm going to put 2 du. So I can put the 2 out front, 2, and then du. Okay, now what's left in yellow? That's an easy derivative if you've memorized your trig derivatives. Secant tangent, that's the derivative of secant. So I get 2 secant of u. Remember, the derivative of secant is secant tangent. So I get 2 times the secant of u, and then now just put your, instead of u, put the definition of u back. So u is equal to the square root of theta plus c. All right? So sometimes what you want for your u substitution is an angle itself. And that's it.